Well, welcome to this keynote session to be presented by Dennis Kai from Alibaba Cloud. I'm Bruce Davey, the General Chair of the P4 workshop, and I'm very excited to have Dennis joining us here to present on his experiences with using P4 and programmable networking more broadly to deliver predictable network services in the Alibaba Cloud. Dennis is the head of network infrastructure, and I feel like we don't hear enough about Alibaba. It's an absolutely massive cloud service, very important in the part of the world where I live, which is the Asia Pacific region. So great to have Dennis joining us. And without further ado, I will hand over to him.
Thanks, Bruce, for the introduction. And hello, everyone. I'm Dennis Kai from Alibaba Cloud, and I'm very pleasure to be here. In my talk, I will share with you our journey towards a predictable network. I will explain what we mean for the predictable network. Many of this work are strongly related to programmable switching ASICs and NICs, and some of them are P4 related. First, I will talk about our data center network. Then I will share our network for the edge cloud. And we are open to share, and we are also looking for some suggestions, discussions, and potential collaborations with you. First of all, as we all know, there are many changes in this world in the past 2 years, and there are many uncertainties. But one thing is certain, the world is accelerating into digitalization. Let me introduce my company a little bit. Alibaba started as a web company. Alibaba Group is such company who is helping our customers for digital transformation. Alibaba Group's mission is to make it easier to do business anywhere. And our vision for the fiscal year 2036 is to have 2 billion of consumers and 10 millions of businesses and 100 millions of jobs over our platforms. As you can see on the right hand, these Alibaba ecosystems, we have very rich business landscapes across e-commerce, local consumer services, digital media and entertainment, logistics, and so on. And all of these businesses are digitalized and running on top of the Alibaba Cloud. Alibaba Cloud global infrastructure, as of today, we have 27 regions and 84 availability zones, over 100 data centers, and 2,800 edge nodes, over 6 continents. Alibaba Cloud is helping our own businesses and our customers to accelerate into the digital world. The digital world is running on top of real servers and which are connected by network. Today, the network is well beyond what we know network 2 decades ago. Network is dramatically evolving in the last 20 years from many angles. For the first 10 years of this century, internet is blooming, and more people and companies are connected. It is the era of the internet connection. So the second years is era of the web applications and the mobile internet. The web scale drives the network architecture evolutions. We enter into SDN, software-defined network time. So we all know what happened, right? The motion silicon, white box switches, virtualizations, open and disaggregation, scale out architecture for max scale DCs, network automation become a must. So today, it only take a minute to create a global virtual network for a particular enterprise on the cloud, which will take a few months or even more in the past. So network had advanced a lot in the past 2 decades, but what's next? So what the network looks like in the next 10 years? So we believe cloud will become a new public infrastructures, just like water, gas, utilities. So the cloud network as a new public utilities, it must be highly reliable. The resource must be able to be shared in a secure and efficient way and open to the public. So more important, the quality and the performance of the network must be predictable. So what's a predictable means here? Just like when you turn on the switch light or the faucet, you know what will happen. This is, we call it predictable. But during the rush hour, if you drive across the cities, you can't predict, how long it may take. So today, we're still suffer a lot from our network quality and performance, even though it has been improved a lot. When we look for the next 5 to 10 years, we know cloud will expand the coverage from central to the edge. The mega scale will move to next level. So today is about millions of servers in hundreds of central data centers. For next 5 to 10 years, it will be millions of the servers over 1,000 or tens of thousands edge size. So for the workload, the AI and the big data will dominate. We need a high predictable network performance to scale out the GPU clusters or storage. Fundamentally, we need to reduce the communication tax and give more computing power to the applications. The cloud business and application bring in a tremendous challenge to our network, which will require technology innovations. Fortunately, there are lots of innovations happening today, especially from the hardware point of view, like programmable switch ASICs, smart NICs, RPU or DPU, whatever you want to call. So we believe for the next 5 to 10 years, we will evolve towards a predictable network. Besides this super reliable and secure operational efficiency, low cost, it must be able to provide a predictable performance. So next, I will share with you our journey towards a predictable network in Alibaba Cloud. First, I will talk about our predictable DC network. Then, I will share with you our edge cloud. To start our journey for the predictable DC network, the first step is to build a modern max-scale data center network. Similar to what the other bigger CSP did, we simplified our data center network design with a scale-out architecture using single-chip switches. And the switches are white box based on the OpenSonic. And the softwares are fully in-house developed. So the networks have been running more than 3 years in Alibaba Cloud, and the result is fantastic. It is very stable and highly efficient. However, this is just the foundation towards the predictable network. We are still facing a lot of challenges, especially from performance perspective, due to the big data and AI workload. In our data center, we use disaggregated architecture for the compute and the storage deployment. We have high performance storage cluster. The storage evolved very rapidly from HDD to SSD and to the persistence memory. The storage latency has reduced, from the milliseconds level to tens of microseconds level. Now the network become a new bottleneck. So it requires not only the high bandwidth, but also the low latency, and more important, to avoid the slow I/O, we needed to reduce the tail latency. Next scenario is HPC and machine learning. For the big AI training models, for example, it requires a large AI cluster to connect hundreds or even thousands of GPU cards together. It's very critical to optimize network performance to reduce the communication overhead, or we also call it communication tax. So in today's DC, we have different server CPU, server skills. We have a server for ECS, server for storage, server for GPUs, right? So it is a disaggregated architecture for our compute and storage, as I mentioned earlier. So as a next step, with the predictable network performance, we believe the data center architecture will evolve from disaggregated model to fully composable, so to create a much more efficient resource pool. To achieve the predictable performance for both latency and bandwidth guarantee, it is not easy. It is very difficult. So we made some progress in the past few years. I would like to share some of the work here with you. I will describe this from bottom up. So at the silicon level, we need network monitoring capabilities to quickly mitigate the network performance anomalies. So we work with switch vendors, switch chip vendors to implement flow event telemetry monitors. So this can detect the flow level events such as a packet loss, you know, packet congestion, latency change, and etc. So at a network fabric level, today there's no guarantee on the connectivity bandwidth and latency at the microseconds level. And we did some experimentals, which we will publish to this year's SIGCOMM. So the paper describe how to build up a predictable microfabric use a programmable data plan. I will take a little more detail in next slides. Okay. At a transport level, neither the UDP, TCP or RDMA can achieve the ultra-low latency, high bandwidth, and stability simultaneously. It requires advanced network congestion control, and we did some of this work back to 2019, use inbound network telemetry for precise congestion control. And now we call this HPCC, and now HPCC has been widely deployed in our network. So I think just a network is not enough. We need application and storage co-design. We also call application optimizations. So we did quite a lot of work with network and storage co-design. So based on what we used like a Rocky, a few years ago, and we developed a new UDP-based low latency, high performance network protocol, which we call SOLA. And SOLA has been deployed in our network, and it tied together with HPCC congestion control and multipass, as well as with this the network microfabric, which I mentioned earlier. So we tie all this together so we can achieve much better latency for our storage applications, especially for the tail latency, and especially when there's a network failure happen. Okay. And this work we also we're going to share with the public through this year's SIGCOMM paper as well. So besides storage and the network co-design, we also did some work with our HPC, the machine learning, the compute and the network co-design. So that work, actually, we did publish this like 2 years ago. So next, I will talk a little bit about this microfabric work. So as we all know, in today's max-scale data center, we typically use ECMP for packet load balance. So the ECMP is hop by hop, and we often run into the hash polarizations, and the link bandwidth cannot be evenly used. So when this is often fine for the traditional data center workload, but for the big data related workload, like a machine learning, storage, as I mentioned earlier, we need a more evenly packet distribution, not only for the efficient bandwidth usage, but more important for the latency and for tail latency. So I would like to share with you one of our recent work about this predictable microfabric. It is still in the experimental stage, and we are open for the discussions, with anyone who is interested. So we call this predictable microfabric, which really means the edge node, you can adjust the network path at a microsecond level for better bandwidth and latency. The fabric, including two parts, as you can see here. One is called U-fabric edge. Typically is a SmartNIC, RPU or DPUs. The other part is called U-fabric core. They are typically switches. This is a fully distributed systems without the need any central controllers. So the edge node send the probe packet to the selected multipath between each others. The probe will carry all the informations from the switches along the path. Then the edge node will choose the best path. Meanwhile, the edge node will register itself to all core switches along the selected path. So in a normal situation, the switch will summarize the total bandwidth subscriptions on each link and also the link usage and pitch back this information, to the probe packets. So when the edge node detects, it cannot achieve the target bandwidth, it can trigger the probe packet, to reselect the better path if possible. So when their network failure or congestion happens, the switch can add this information to the probe and send it to the edge node. So this is just a basic idea. It is much more complicated than that, and certainly is it is still in the experimental stage, right? It's in a more a real deployment to prove that. So the basic idea is similar to uh, traffic engineering, what we use in a wide area network, but it dramatically simplified, and we try to apply this to the data center network using a programmable switch and the NIC. Okay. So if you have interest in this, certainly you can attend this year's SIGCOM conference. Well, that's the DC network. Next, I will share with you some of our work for our edge cloud network. I think most of people here are familiar with the term like edge computing, edge cloud. It is a natural idea, if you can bring cloud service to the end users, close to the end users, they will enjoy the low latency and the lower traffic costs to access computing resource and services. So people talk about edge computing for a decade, right? But the commercialize of the edge cloud did not start to fly until very recently. Due to the COVID-19, the cloud gaming and video conference become very popular. Use a cloud gaming as example. Like many users, they are still have very cheap phones, and it's a perfect user scenario for the edge computing. Right? They can move this GPU workload to the edge cloud for the gaming. Right? So meanwhile, the 5G network become more and more popular, which can provide much better last mile network performance. So with both applications and the technology readiness, we can see the edge cloud business is reaching a golden point, which will fly. There's business for the edge cloud. Then why not just do it? But unfortunately, it's not that easy to scale down. So many people may think, if I can build like a bigger cloud, right, like tens of thousands of data center, probably it's easier to build a small, like hundreds, kind of a small edge site. That's not true. Okay. So edge cloud has its own unique challenges and requirements as well. So which will need dedicated ideas and solutions. So first, the edge cloud applications need high performance, like a video streaming need a high bandwidth, like a gaming will need a low latency, as well as computing power in the cloud. And the second, for the edge applications like a gaming, the customer typically want to keep their own kind of customized kind of servers for the high performance for differentiations, right? Because of this, it's very difficult, you install our cloud software stack into these servers. So it's a very low host intrusion. Last but not least, for multi-tenancy, right, it needs isolation and secure. So they need to share the resource. So the traditional virtual network like VPC, firewall, load balance and so on. So those functions typically running on the host or on the gateway will consume resource. on the servers. People also call this a cloud tax. So for edge cloud market, especially here in China, it's a very competitive market. So the cost is very sensitive. The ROI is important. So we need a very competitive solutions for the cloud infrastructure. So then how to provide the solution for the edge cloud? So one option is to install the cloud stacks, such as a virtual switch on the servers, which, as I mentioned previously, this is very difficult due to the customized hardware and low host intrusion. The second option, to have dedicated host to run the cloud stack, which may require quite a few servers, even for just a small edge size. This is not a good ROI. So for our solution, sites for the P4 programmable switch ASIC, we combine P4 ASIC and the computing resource together and create a new network gateway to run the cloud stack. So which makes this edge cloud business possible from both technical and from business ROI perspective. Our solution is called SNA, which stands for a smart network appliance. It is an in-house designed and built a high converged performance gateway. Let me describe this a little bit here. So at the bottom is the hardware. It is a P4 switch ASIC, and with a server CPU plus have FPGA as extensible option. So we offload layer 4, layer 7 function to the P4 switch ASIC as much as we can. But there are some resource limitations, especially in this fourth generation P4 switch ASIC. So we need to use FPGA for big table size for some user scenarios. And we also need a server kind of powerful CPU to handle some logic which cannot be done by the P4. And also for some like stateful layer 7 gateway functions using software. So on top of the hardware, we run our Sonic based switch OS. This SNA gateway has the 4 switch functions. So in addition, we also have network virtualized function like this ERP, NET, load balance, firewall, and so on, running on this same hyper converged device as well. Because we have all these functions converged together, so we do have this orchestration systems and table management to optimize resource sharing among these layer 4 to layer 7 functions. And also we provide SDK for our internal customers. So they can run their own kind of network functions like load balance, net, firewall on our SNA platforms. So SNA, as you can see here, they have mixed the switch and the layer 7 NFV functions together. That's why we call it hyper-converged network gateway. So the SNA has been deployed in Alibaba Edge Cloud. Right now it's over like 300 to 400 sites already today. Well, let me also share some experience for our SNA development and deployment. It is not easy. There are many challenges from the coding, compiling, debugging, testing, and even for the deployment. So first is coding. P4 is a low-level language. There are lots of hardware constraints. You need to know the hardware architecture very well. So when you move from the one generation to another generation or move to different vendors, you will need to rewrite the code. And the compiling is also some challenges due to the premature compilers. So when there's compiling errors, our developers often don't know what's the reason. And also they are lacking of debugging tools as well. So for the code debugging, compiling debugging, and even for the performance, we are lacking of the performance testing tools. Okay. Last but not least, we run into the issues for the deployment and management as well. So as a simple example, so how to manage this device, right? Is it a server or is it a switch? So we have very mature management systems for the server and also for the switch, but they are separate systems belong to different teams. But for the SNA, we have to, develop and enhance our operation management tool, for this a new device. That's why people also call this a server switch. So we run into all kinds of issues, and also we invented quite a lot of solutions and solve the problems, and we publish all this information into different papers, and want to make it open and to share with these ecosystems. Okay, so the good news, as I can share with you, so today SNA has been developed like over 3 years, not only in the edge cloud, but also work as a high performance network gateway in our central DC to replace x86 based gateway to support super large, customers in the cloud. For example, to support Alibaba Group itself. So I mean, this the bandwidth and the performance is much higher than what the x86 can support. So I just shared some of our work in both central DC and edge cloud. So to conclude my talk, the world is accelerating into digitalizations, and cloud computing is become a new public utilities to support this digital world. And the cloud network is well beyond what the traditional network can support from many angles. And our vision, network is evolving towards a predictable network. So with the new emerging technologies like end-to-end programmability, P4, switch chips, and the NICs, and certainly the P4 ecosystems, we fully believe this predictable network will become possible. And in Alibaba Cloud, we already start this journey 5 years ago and made some solid progress. And we are still working on this. This is just the beginning. So finally, this is my talk. Thank you for listening.
Yeah, so Dennis, thanks very much. That was really great. I do have quite a few things I wanted to talk to you about. First of all, I want to say it's so great to see all the pointers that you've given to all the academic publications at SIGCOMM and NSDI and other conferences. And so obviously anybody who really wants to go deeper on this has got places to go to learn more. So I'll just make sure that everybody's aware that they can go track down your work across all those conferences. The thing that I think probably jumped out to me the most was this focus on how to build a sort of cost-effective solution for the edge cloud. As you said, edge clouds have become quite a hot topic. I think lots of people recognize the value of taking the cloud services and moving them out closer to the edge. And so I guess my first question is, what was the critical thing that made you realize you needed programmable infrastructure running at the edge? Because if I look at a typical cloud, a typical edge cloud, to the extent that there is such a thing, we probably often expect to say, well, it's going to have some servers and some switches. Why did you feel you needed programmable switches for the edge cloud?
Well, today, when we look at the edge size, even though the size is small, but from the functional point of view, it's like a full stack, right? You need a traditional switch, right? You need this virtualized functions like load balance, like net, right? This and so on. So if we just use a traditional, like what we did for the traditional cloud, we will need a couple of switches there and a bunch of like servers there. And but for our edge cloud deployment, a lot of case is only just like a one rack there. So for some small size, so it's only probably have like a tens of server. That's it for one rack. So that's not space for that. I think that's the number one. That's one of the main driver for that, right?
Yeah, so this is really interesting, right? So
yeah.
So you need kind of a full network stack, and the only way to do that with sort of traditional equipment would be to have a traditional switch plus a bunch of x86, which actually has a very large footprint. Whereas what you're able to do is you can come in with this appliance that has just the amount of programmability you need for network functions because that's what P4 is designed for. So to me, it's always interesting to see kind of how P4 lets us go in directions we might not have necessarily expected. And this is one for me where, it's not that you could not have done this any other way. It's that if you had done it any other way, it would have had a much bigger footprint, which, is maybe almost a deal breaker in the edge cloud environment.
Yes, yeah, certainly, yes. Yeah.
Yeah.
I mean, certainly,
Those are,
yeah, certainly besides that, right, there's a lot of some, I would say, unique functions with the P4. On the edge side, we're also on some like DDoS attack. So we can program some rules into the ASIC level, do some kind of filtering, and they can give a much high kind of bandwidth protection for some of the DDoS attack. So
yeah.
they do have some unique functions which cannot be done by the x86 software.
Right. Yeah. I mean, and I think so that's another good argument there. It's and I think like it's always, it's interesting to see somebody trying to tackle this kind of commercial market where, you have to pay attention to the cost of things. And I think it's one of the areas that I've always said as a networking person, you have to pay attention to what things cost, because if we didn't care about cost, we might never have done packet switching. And so, there's a sense that like we're always looking at the theoretical capabilities, but we're also trying to make sure we do them in a cost-effective way. And I think P4 has been really successful in that way. So one of the things I took away from the talk was that there's really an importance around tooling, and I wonder if you could just say a little bit more about like how the need for tools kind of plays out in your environment.
Yeah, so to make this P4-based gateway really can be deployed in large scale, actually we need a lot of tools. So the first tool, and I mean, certainly these tools are not available in the market today. We are kind of like a pioneer, right? So the first tool we build is a combiner, okay? And this tool is help to detect some errors when combine this P4 language. And I think that's the one tool. The other tool we build is actually for the performance testing. So and today, I mean, there's not kind of even testing tool to do that. So we have to use build a P4-based ASIC to build this tool for performance testing as well. Besides that, yeah, I think that's the two actually major two we made. Yeah.
I mean, I think there's a really important point here, and like I remember noticing this when I first started paying attention to the P4 space, is that people think of it as being a language, and there's a switch architecture, but ultimately it's having a complete software tool chain that makes this usable. And I think one of the takeaways I have from your talk is we're still in a quite early stage in terms of developing those tool chains, and I guess that's an important thing for this community to realize that that's an area for more investment. And you can see, Intel as an example is, making quite a lot of investment in developing tooling around P4. And I think it's good for this community to know that like that's an area where it's not like we've solved everything. We need to invest more there. Maybe just one last more general question I'd like to ask you. You've found a lot of applications for programmable networking, both in your data center and in your edge. Do you think that over time, we just keep on needing to have programmable infrastructure? Or is it that as we learn what we need, those programmable functions might move into fixed hardware? So do you think, does the network always have to be programmable, or could we over time sort of solidify the programmable functions as more fixed functions?
I think this is a very interesting question. I think Bruce, as you know, we also have this kind of debate in our team as well. So people always say, programmability is not is not for free. That's not free
Hmm.
lunch, right? So I think the discussion is around the programmability versus performance versus economics, right? I mean, from economy point of view, I mean, we all know, there's many factors for the cost for the switch chip, right? I mean, certainly, like for example, the volume is like make a big difference. So I think that's not my concern, right? I think really from the application point of view, I would say today's application, they are evolving much faster than what we expect. I just give you one example, right? So only a couple of years ago, we tried to use RDMA. RDMA is like a low latency kind of high performance kind of technology, right? We use RDMA for our storage. At that moment, the storage cluster is only about like 100 server, and we use this like a lossless network, use a PFC for the flow control, and go back N for the packet retransmission. It seems all this like a fixed function in the server NIC, right? But only after maybe 1 or 2 years, and this low latency network become much more popular for machine learning. This training these big models, right? So now we have to enhance a lot, doing a lot of code designs there. So we have to invent, this, high performance congestion controls and with code design, with storage, with compute, and with multi-pass, a lot of new enhancement. And then, when we work with the switch NIC vendors, with it's a fixed function. A lot of things we cannot do. We have to wait for next generations. But the good news is for the next generation, pretty much all the server NIC vendors we work with, they develop a certain level of the programmability there, and to make all this function to be implemented possible. I think that's just one example. And in some other areas, like when we do the network programming for the security, for all kinds of policies, is all required dynamic changes there. So
Yeah.
I don't I think this fixed function is not is as false like statement in my opinion. There's always something new come out.
Yeah.
Yeah.
Well, look, great. I think that's a nice way to end it. I think that kind of gives us a good sense of why programmable switching hardware is probably here to stay for a long time, and that's a good message for this community. So I think we'll end it there. Dennis, thanks very much for a really interesting talk. It's great to get the insight into what you guys are doing there with all the innovative things around both your data center and your edge clouds. And I encourage people who want to learn more to go and read some of those SIGCOMM and NSDI papers you've been publishing. And thanks again for a really great talk.
Thank you, Bruce.